Hi guys, for today's video we're going to be taking a look at ways that we can use some of the trigonometry knowledge that we've gained during this chapter to do some application problems or word problems. And we're going to jump in with taking a look at a term or some terms that you're going to see in some of these word problems that I need to make sure you understand. A lot of these word problems are going to talk about angles of elevation or depression. And all that means when we're talking about, for instance, an angle of elevation, what will typically happen is there'll be somebody who is looking up or sighting up at an object that is above where they're at. And the angle of elevation would be the angle where if we made a line that is completely horizontal from their eye line, and then the other side of that angle was like the path that they'd be looking along to see the object. Those two sides would make an angle, and that angle measure is what we call the angle of elevation. Now the angle of depression, the only difference is instead of looking up at an object, we're looking down at an object. But again, we're going to imagine that we have a segment or a line that represents eye level. And then we have another segment or line or ray that represents our line of sight going down to the object. And those two lines or rays would be making an angle, and that angle's measure would be what we call the angle of depression. So if we look in this picture, just to kind of help you understand a little bit how this might end up being used, we have this picture where we have like three people, right? We have the person that's up by the restaurant, we have the person that's on the observation deck, and we have the person that's down here at ground level. If we had the person at ground level looking up at the person in the observation deck, the angle of elevation would be angle 4 here. Whereas if we had a person who's at the restaurant looking at the person of kind of at the observation deck, there would be an angle of depression right here at angle 1, because we have their eye line and then that line that's representing their line of sight, and so that would be an angle of depression. Now there's an interesting question here. It says, how does the angle of depression number 1 compare with the angle of elevation for angle number 2, right? Because angle 2 is an angle of elevation from the observation deck looking up at the restaurant. Angle 1 is an angle of depression for the person at the restaurant looking at the observation deck person. So but what about these angles? What's interesting about that? Well, if we think about the eye lines of each one of these people, those eye lines are meant to be completely horizontal, like perfectly horizontal, looking straight out. And what that means is they'll be parallel to each other. This eye line and this eye line, and technically this eye line down here would be all parallel to each other. So this line of sight right here would be like a transversal going across two parallel lines. And that means angle 1 and angle 2 would be alternate interior angles. And that would make them congruent, since when we have a transversal going across parallel lines, those alternate interior angles always end up being congruent. And that idea is going to be important in some of the questions that we're going to look at. So angle 1 and angle 2 would be congruent. Angle 3 and angle 4 would be congruent for the same reasons. Again, this line of sight would be a transversal cutting across this line and this line, which are parallel, and that would make these alternate interior angles congruent. Now, moving in a bit of a different direction, we're going to take a look at a triangle, and the question is asking, how could I use trigonometry to find the area of this triangle? Now, you've learned several years ago that to find the area of a triangle, we take 1/2 the base of the triangle times the height of the triangle. And the base of a triangle can technically be any side of it, but we'll think, for this triangle, we'll think of it as this side here, since it's kind of already labeled as B. All right, the base could be any side technically. The height of the triangle then is the distance from that base across to the opposite corner. So if this bottom part is the base, then the height would be the distance from point B to the base. So we would have to actually draw in an additional segment here to represent that height. It would look like this, right? And the height will be perpendicular to the base. Now, if all I knew was side lengths A, B, and C, I might not initially think there's any way for me to find the area of that triangle. If I'm not given this height length, basically, what I'm saying is if I was not given this height, the length of this height segment, it would initially seem like I would not be able to use this area formula. But if I had some other information about this triangle, For instance, let's say I knew how long B was and how long C was, and I knew this angle right here. Okay, let's imagine that I had that information. This length, and this angle right here. If I think about what how H could be represented differently in this triangle, I might come up with a way that I could actually find the area. Because this H right here is a side of a couple different right triangles now in my picture. This right triangle and also this right triangle here. So if I look at this angle and this right triangle, I would be able to say that, get a color here, I would be able to say that the sine of angle A would be equal to H over C, and that's just using the idea of SOHCAHTOA, right? I could also say that the sine of angle C would be equal to H over A, and both of these work because in this representation, I'm looking at this right triangle. C would be the hypotenuse of this right triangle right here. H would be the side opposite angle A. If I shift over to this right triangle, A is the hypotenuse, H would be opposite angle C. So if I look at angle A and I say sine of angle A would be opposite over hypotenuse, that would set up this equation. Or sine of angle C would be opposite over hypotenuse, that would set up this equation. Now if I take each of these equations and I isolate the H in them, let's look and see what happens then. I would have H equals C times the sine of A. And over here I would have H equals A times the sine of C. And if I go back to my original area formula, remember B is this side right here, I can now replace this H with either one of these two expressions. So I could say that A now equals 1/2 times B times C times the sine of area A. And don't get confused here. I got two capital A's. I got a capital A here and a capital A here. Maybe what I should do is, maybe I should represent this as saying by area instead of A, so it's not as confusing. I'll say area equals 1/2 this side times the sine of A. Or I could say that the area equals 1/2 times B times A times the sine of C, right? Either one of these equations would work based on, just depending on which information I had. I'd have to know this B side, and I'd either have to know both C and this angle, or both A and this angle, but in either one of those scenarios, I could take those measurements, BC and angle A, or BA and angle C, and I could plug them into one of these formulas, and I could get the area that way. Now, if we expand that idea and we maybe shifted to one of the other sides, either A over here or C over here being considered our base, we would actually also be able to use the same reasoning to come up with a third formula. So this one here and this one here we showed on the last screen. But if I shifted to either C or A being the base, it would also generate this formula here. Bottom line is, these are now new formulas that we can use to find areas of triangles where we don't know what the height of the triangle is. Maybe we only know side lengths, maybe we know some angles. Of course, if it was a situation where we knew all three sides, A, B, and C, we could still use one of these formulas. We would just first have to use the law of cosines to find one of the angles that we could use, right? But it would still be possible. It would just have extra steps if I knew all three sides of the triangle. And so what this does is this opens the door for pretty much any time we know three things about the triangle, including at least one side, right? So if we know a side and two angles, or two sides and an angle, or all three sides, we should be able to use one of these formulas, and maybe also have to use law of sines or law of cosines to find an angle measure that we need, or a missing side that we need. But we should be able to, just having three pieces of information about our triangle, one of which has to be a side length, we should be able to use one of these formulas to find its area.